Theory of everything. How progress in physics depends on asking the right questions. When I began my undergraduate physics degree, around 20 years ago, what is the theory of everything, was a question that I heard often. It was used as a label for how theoretical physicists were trying to develop a deeper understanding of the elementary building blocks of our universe and the forces that govern their dynamics. Why a theory of everything? The Standard Model of particle physics, one of the pillars of modern science, is a success of reductionism, the idea that things can be explained by breaking them down into smaller parts. It explains the nature of 3 out of 4 of the known fundamental forces, electromagnetism, and the weak and strong forces that govern processes on subatomic scales. The model, which is written in a mathematical language called quantum field theory, describes how elementary particles move around and interact with one another. The model accounts for quantum mechanics, which describes the probabilistic nature of the dynamics of subatomic particles, and Einstein's special theory of relativity, which describes what happens when relative speeds are close to the speed of light, no small achievement. It does not include gravity, the fourth force. The assumption in asking, what is the theory of everything, is that the Standard Model will one day be found to be embedded within a larger structure, with more elemental ingredients, that provides us with a unified explanation of the fundamental forces including gravity. Gravity, in fact, is this question's ultimate focus. But the question, what is the theory of everything, gives very little guidance as to what such a theory of everything might look like. We need some better questions. Now, there are good reasons to expect that such a unified explanation of the fundamental forces might exist. The Standard Model includes the celebrated Higgs mechanism, from which the Higgs boson arises. It explains why fundamental particles known as the W and Z bosons, which transmit the weak force, acquire a mass. It also explains why the photon, which transmits the electromagnetic force, does not. In the early universe, the electromagnetic and weak forces were unified at high energies. As the universe cooled down, the Higgs field underwent a phase transition, and its interaction with particles broke the electroweak symmetry, resulting in the separation of the electromagnetic and weak forces into distinct forces observed today. As a result, electromagnetism and the weak force, which is involved in the nuclear fusion that powers stars, behave differently at low energies. The electromagnetic force acts over very large distances, whereas the weak force acts only over very short distances. The Higgs mechanism also explains why, at higher energies, these two forces start to behave as a single, electroweak, force. This is called electroweak unification. Now, if electromagnetism and the weak force combine in this way, why not all the forces in the Standard Model? Unifying these two with the strong force, the force that holds the ingredients of atomic nuclei together, is the aim of grand unified theories. Theoretical ideas such as supersymmetry, which postulates a symmetry between force carriers and matter particles, suggest that the strength of these three forces could get tantalizingly close at high enough energies. And if the electromagnetic, weak and strong forces turn out to be unified, why not gravity, too? Gravity is described by Einstein's general theory of relativity, which applies on large scales or at low energies. But if we want a consistent quantum theory of gravity that applies on the smallest scales, quantum field theory, QFT, isn't enough. This is because QFT is based on flat spacetime, while general relativity describes curved spacetime. This was a challenge to quantum gravity. We need mathematical frameworks that can consistently incorporate both general relativity and quantum mechanics. The everything, in a theory of everything, refers to all the known forces of nature: electromagnetism, the weak force, the strong force, and gravity, and new, hypothetical forces, too, and the particles that they act between. The theory refers to the existence of some common mathematical framework that describes all of the everything. One such common mathematical framework is string theory, which supposes that the most fundamental building blocks of the universe are tiny strings that vibrate in extra-spatial dimensions beyond the three of our everyday experience. Frameworks such as supersymmetry and string theory were not developed to answer the question, "What is the theory of everything?" directly. They were motivated by better questions about what a theory of all the fundamental forces needs to explain and what it might look like. Questions like, why is there a huge discrepancy between the energy scales of the Standard Model and quantum gravity? Why do quantum mechanics and general relativity seem to be incompatible? But the whys that theoretical physicists ask develop as our understanding develops, and the questions that we are now posing are getting us even closer than ever to an understanding of all the known forces of nature. These new whys hint at remarkable connections between very different areas of physics and mathematics. Why does the physics of holograms seem to help us to understand gravity? Why do the rules of quantum information seem to explain the physics of black holes? These new questions have been reached by building on what has been learnt from developing and studying possible theories of everything, like string theory. That is what scientific discovery is all about. This article is written in an easygoing tone based on the scientific method, which I hope will help the general audience understand the scientific method in this big picture. Thank you.